Okay. It basically, if you think everything here looks like it came from the hardware store, it did.
That's how simple it is.
Yeah, tell us what we're looking at right now, sir.
Yeah, this is a 3/4 inch brass pipe nickel. It's about 4 inches, 5 inches long. Got a end cap here, a bushing here, and then a nylon bushing at this point. And coming down through the top is a 1/4 inch copper tube, like what you use to hook up your ice machine on your refrigerator. And it comes down about this far down. And that has been co-deposited with palladium. The nylon provides electrical insulation between the working electrode, which is the palladium, and the brass pipe. The various fittings that you see here are so we could, when we first started, we would pull a vacuum on everything, close this valve, open this one, and put a couple of drops of D2O in. And prior to that, we would have put a little piece of lithium that we extracted from a rechargeable battery in the bottom, close this up, lock, and then drop the water down onto the lithium where it would react and produce deuterium gas. And that was the deuterium gas then that filled the cell. When we closed everything up, and we could monitor the pressure and everything. This particular cell, the reason it looks so rusty is it's been operating
in excess of 8 years.
Yeah, in excess of 8 years, somewhere around 2014. Yeah, it was operating 2 minutes ago when I went out and picked it up. The reason we don't have a lot of cells here is we just took a whole box of them up to this conference, and Harper showed you the one of the simple electrodes that we took up, and we had a table set there at the conference where people could come up and with a simple voltmeter and attach the voltmeter to this screen, which here have the negative from the voltmeter attached to a piece of steel that's coated with zinc or a piece of zinc, and you put the two together and you measure 6 to 7 tenths of a volt. And people came up, we missed most breaks because when there ever would be a break, we would be out at our table and people would be there. And sometimes I'd go out there and people were conducting their own experiments, and because it shouldn't happen, it's unexpected. And in fact, the only way something like this can happen is there have to be ions present. And the question is, where do ions come from? Well, then the gas is normally considered a non-conductor. It's actually a very, very poor conductor unless it's a pure dry gas. But so we had to eliminate all of those potential sources of where the ions were coming from. And the bottom line is you come to the conclusion that the palladium electrode is producing ionizing radiation. And that is the surprising aspect of this.
But when you try to measure the ionizing radiation, all attempts to date have proved unsatisfactory, that we have made and that other people have made at various parts here in the United States or overseas. And this is what then becomes the underlying problem of the physics, because how can you be ionizing the gas and not being able to measure what it is that is ionizing it?
Yeah, BARC, the Bahaba Atomic Research Center in India, which is their equivalent to Lawrence Livermore Lab, so on. In the 1990s, they discovered that these electrodes that they made would ionize film, or they would fog film. So they thought, well, gee, that we've got instrumentation here that's orders of magnitude more sensitive than the film. Let's see if we can identify what it is. They published several papers, and basically in their last paper concluded that some unknown agent must be ionizing the film because they were unable to identify it. They used all sorts of different filters and everything. In fact, that paper is available and we can send it to you to take a look at. But the bottom line is they didn't detect it. Currently, one of our collaborators who recently retired from Los Alamos National Lab, he is looking to see if he can detect the ionization. He's built a cloud chamber. He's done a whole bunch of experiments, and he's only been at this for about 6 months. But as of now, he has not been able to detect any of the ionization. We have another individual who's been one of our collaborators. He's here in Santa Cruz, California. He is looking right now, in fact, and he sent an email just like 2 days ago with some of his preliminary results. At this point, it's not sure. He's still got more analysis to do to see whether or not he's detected anything. But whatever it is, it's very elusive. And we don't know if that's because it's outside the frequency range. Is it above or below the threshold for the sensors or whatever? I wonder, personally, I'm not a physicist, so I can come up with crazy ideas, but I'm wondering if the surface area of the detector is a problem, because it could be such high frequency that may be a problem. So, but I don't know. We'll have to see. But that's the bottom line is we know something is ionizing the gas, and once you have ionized gas, then or have ions, then you have an opportunity to harvest those ions to produce electricity.
Let me go back for a moment and to make sure that we understand why we believe that this is the important thing. Because the fact that gas has to contain ions in order to conduct was first shown by J.J. Thomson in the 1890s. And at that point in time, people did not understand the conduction of electricity through gases. And his work was so notable that in 1906, Thomson was awarded the Nobel Prize in Physics for his explanation of the conduction of electricity through gases. Why this information is not so widely known today is due to the results of one of his students, Townsend. Townsend published his book in 1915, who said that if you run the gas at very low pressure, then what will happen is spontaneous production of free electrons in the gas will become accelerated by the electric field. They will then cause multiple electrons to be produced from other gas molecules, and a cascade will result, which will then result in a large number of electrons being produced. This then became the basis of the fluorescent light bulb and the neon bulb. And so it turns out that now most of the work up until recent time has been devoted to the study of low pressure gases. In the LEC, the device that we showed you, the gas pressure in this tube is of the order of atmospheric pressure, well above the pressure of which the phenomenon that are currently studied apply.
Would you please state your name and background and your title in this project?
My name is Harper Whitehouse. I'm the co-collaborator on the program. My background is undergraduate physics, graduate mathematics, sabbatical electrical engineering.
Okay, I'm Frank Gordon. My background is a BS in mechanical engineering and a Doctor of Engineering degree, and then 38 years working for Navy Research and Development Laboratory here in San Diego. mostly in supervisory positions, ultimately retiring as the head of the Research and Applied Sciences Department about 12 years ago.
What brought you into this journey together?
In 1989, I was the head of the Anti-Submarine Warfare Department at the Navy Lab. And I had two scientists working for me, Dr. Stan Spock and Dr. Pam Boss, both electrochemists. And they were working on the development of high energy density batteries for torpedo propulsion. And the announcement, of course, that's when the announcement was made. Turns out Stan knew Flashman and had actually, I think, maybe even published some papers with him. So he contacted Flashman. They went into the lab. They never did replicate the approach that Flashman and Pons were using. Stan said he had a better way, and he came up with something he called co-deposition. And what that is instead of starting with a solid piece of palladium, you started with an electrode that could be any conductor. Copper, I think, was the initial one that we used. And then you mixed a solution of palladium chloride, lithium chloride, and you passed a current through that solution, and the palladium would evolve at the cathode, which was the copper plate. That's also where the hydrogen or the deuterium would evolve if you were using heavy water. So as you were building up the deposit of palladium, you were loading it with the hydrogen or deuterium. So you're building up a metal hydride, basically. And that was a very important discovery, because whereas Flashman and Pons may take them several weeks before they would find out if they were going to have an active electrode, we could see results within less than an hour. And also that gave us tremendous flexibility. We could actually attach a thermocouple right to the back of the copper, have another thermocouple in the solution, for example, and measure the temperature difference. We could see the temperature elevating in the electrode where it was hotter than the temperature of the solution. And if it was ohmic heating, which a lot of people were claiming that's what was being seen, then the solution, which has a higher resistance, should be warmer than the copper, which was, had a low resistance. That wasn't what we were seeing. So that was the beginning. And
what year was that when you were seeing these results?
About 1989.
Okay.
And we published papers starting about 1990 or 1991. Over the next, until I retired. At the time I retired, we had over 30 published papers in peer-reviewed journals, a lot of presentations, by that time, a lot of people were using co-deposition as the approach to preparing the electrode. And I had been the supervisor. So, the last thing a scientist wants is a supervisor down trying to twiddle knobs in his lab. So I would go down and watch what they did, and sometimes participate in the discussion and experiments. But after I retired, I decided, I want to get somebody and start working on this full time. Harper had been one of the senior scientists on my staff he had retired a few years before that. And so I contacted him and asked him if he wanted to work with me to see if we could figure out what was going on in cold fusion. His answer was, well, I'll let you explain from here.
Well, first thing I did was I said I wanted to review the results at that point in time, which was circa 20, mid 20s.
Yeah, the first thing he said was, I don't believe it's real, but I'll take the time to review the results.
Okay. And he showed me such convincing results that I said, fine, let's go ahead and do this. And of course, the first thing we did was we sat up and we set up some experiments to duplicate now in our own laboratory facilities of the work that had been done, which was a liquid electrolysis. Let me make sure that we understand. Hans and Fleischmann and the work at Speywer was all liquid electrolysis. And yes, indeed, it looked good. And we even thought at one point in time that we were able to detect possibly some neutrons being emitted from the specimens. However, at this point in time, everybody was essentially looking for heat, and they called it excess heat for reasons that are not quite clear when you stop and think about the physics. But nevertheless, the goal was to find this extra heat that was supposed to be emitted by the LENR process. However, if you're going to do something practical with it, you would like to be able to operate at higher temperatures, because it was known at that time, and it's been verified in our lab since that time, that the output of one of these devices increases exponentially with temperature. And so if you want to get a significant amount of power out, in other words, you want to try to solve the green energy problem with this type of a device, then it became clear that one would need to go to higher temperatures. And for this, we chose to go to gas electrolysis rather than liquid electrolysis. Now, the problem is that it's very hard to instrument the temperature of a gas. It was easy, as Frank explained, to instrument the temperature of the electrode and the temperature of the liquid. So I suggested that we try an alternative approach, that what we do is we measure the current through the cell as an alternative to trying to measure the temperature, because it is known that the gas has to be ionized. That was what Thomson got the Nobel Prize for, and that then became the basis of our work. And in the course of doing this, we observed unusual phenomena. Thomson, very well known. However, he was blinded by a preconceived notion that the voltage should be very large applied to his experiments. And under this condition, he therefore dismissed diffusion as one of the variables that determines the performance. And it wasn't until a gentleman by the name of Ricci in 1903 published a mathematical paper in which he wrote the complete set of equations necessary to describe the conduction of electricity through a gas, including diffusion. This work was published in German and simply did not get disseminated. Also, he, with purely mathematical analysis of the electric field distribution within the gas, drew no further conclusions. It wasn't until 1932 that K.K. Darrow, who worked as a research physicist at Bell Telephone Laboratory, published a book in which he gave a complete analysis and drew conclusions about the conduction of electricity when you consider also diffusion. And it is at that point that he then explained the unusual behavior that we observe in these devices. And we believe at this point in time that this is the correct explanation, and it depends upon the fact that you have multiple types of ions within the gas, positive ions, negative ions, caused by this unknown radiation that's ionized the gas, and it is their difference in conduction. The negative ions move more rapidly than the positive ions, and that is what gives rise to the observed voltage that we measure, and we verify then that this in fact increases exponentially with temperature.
So this is producing voltage continuously, is that right?
That's right, but more important than producing voltage, it produces voltage and a current, because power is the product of the voltage times the current. And if we put a very low resistance on the cell, we get a current only, but no power. If we don't put any resistance on the cell, we get a voltage, but no power. But when we load the cell to an intermediate value of resistance, we then get power. So we get, and of course, it's power that we want if we are going to be able to distribute it and other people are going to be able to use it.
And what's the power you're measuring here?
Right now, the power is approximately 1 microwatt per square centimeter of surface area. That now needs to be increased, of course, to get practical power out. And Dr. Gordon presented a paper where he gave 5 methods by which one can improve the power efficiency. Please take over and explain.
Okay,
And this was Devin at the ICCF 24 event
that's correct.
that just took place for listeners' perspective. This just took place in Mountain View, and Dr. Yu and I were going to attend, but then we had something interrupt with that. But we were able to watch some of it online as media. So I just want to give you that context that we've been watching this conference, and this is where Dr. Gordon presented this new paper to 5 ways to scale this power up. Is that right?
Yes, with 5 target ways, and in fact, I had been assigned or given 30 minutes for a presentation, and then there were 2 20-minute presentations by people who had replicated my results. And so what we did was I gave an initial introduction on the evolution of the lattice energy converter. This was suggested by one of the people who was there to, how did we end up at this point? Because there were lots of surprises along the way. And then once we had that, and it is at the end of that 5-minute introduction, there was a 1-minute video that showed me assembling a lattice energy converter and showed it producing a voltage. That was 1 minute from what had been a 5-minute video that's in one of the other presentations. But I wanted to keep my presentation, initial presentation, to 5 minutes. Then 2 people who had replicated, Antonio Di Stefano, who's a scientist in Sicily, he had independently replicated, and he had also written a very nice report where he went through all of the possible other features or the other things that could have contributed to this. How much conduction would you expect through a gap, an air gap of that much, and so on. Anyhow, he did all those calculations and then presented his data. And then John Paul Bavarian, who was actually the first person to replicate the device, he gave a presentation and he talked about the initial replication and some of the experiments he's done since that time show that it does scale up with area. So anyhow, and then when they finished those 2, then I came on back and I had about a 15-minute presentation on the 5 areas to scale up. And in each of those areas, we had experimental data that showed what we could do. For example, the first one was we think we can improve metallurgy. And that's probably the one that we think is the most important and probably where we have the least data. We believe, based on some of our experimental results, that the ionizing radiation is not being produced uniformly over the surface of the electrode. So if we understand how to do it, then we believe we can increase that. And I think I said that might be 1 to 2 orders of magnitude there. We need 6 to 10. Pressure is another one, and we think we can get one order of magnitude there. Improving the harvesting of the ions. When we apply a potential between the electrodes, we sweep out over a milliamp of current. When we have the the spontaneous self-conduction, where we have a very low voltage or only diffusion, we're only conducting a few microamps of current. So better harvesting we think we can get 2 to 3 orders of magnitude. Temperature is an area where we've done experiments. We've shown that we can go 4 to 5 to actually 6 orders of magnitude, going from, say, room temperature of maybe 25 degrees C up to 180 degrees C or 185 degrees C. And then the last one is probably the easiest or most straightforward, and that is increasing the surface area. And the first cells that we built were all designed based on the pipes and so on that we held up. That, you know, this new cell, you can see here how thin that is. It's only probably 1 millimeter thick, and so complete with a separate counter electrode, you're probably talking about 2 to 3 millimeters at most. So you could immediately see how I could stack a lot of these. If I can go from, you know, Harper said we do about 1 microamp per, or 1 microwatt per square centimeter. If I can go to 1 square meter, that's 4 orders of magnitude. And so when I added all those up, I said we needed 6 to 10. I came up with, we had a target. If we met those targets, we would have somewhere between 10 and 14 orders of magnitude. So now, admittedly, those are not all independent variables. Temperature, for example, increases the number of vacancies. Vacancies increase the output of the surface. So they, you know, they're not all independent variables, but I think we still have reason for optimism that we can scale up. The other interesting thing is the approach of using radiation for a battery has been around for a long time. There are numerous patents going back in the 1950s and probably even some before that, where they talk about producing a direct conversion to electricity. Problem is, the only option they have to scale up is to increase the radioactivity. And there are currently, there's currently a company in Florida that is building or working on and advertising a nuclear battery that produces, they have a target for a new one they're building that will produce 100 milliwatts for 10 curies or something like that of radiation. And so to get that up, to scale that up to 1 amp or 1 watt of current, it takes several thousand curies of radiation. And that has been the Achilles heel of nuclear batteries. And so if we have a way to produce ionizing radiation that doesn't require radioactive materials or naturally radioactive materials, and we've seen all of these other ways to increase it, we're optimistic that this might be something that could become an energy source.
Let me break in comment here, because we've mentioned the word battery. Batteries typically produce a voltage, and you put a load on them and the voltage essentially remains constant, independent of the amount of current that you're drawing from the battery until you exceed the capacity of the battery to supply that current due to its internal impedance. The LEC, or the Lattice Energy Converter, is unusual in 2 respects. First of all, it behaves phenomenologically. I can't say that it is, but it behaves as if it is a current source, not a voltage source. And therefore, from an engineering point of view, you have to rethink your engineering, because you are dealing now with something that is not really a battery. And so a lot of people call it a battery. They think it's a battery, but it is a current source that will deliver a current to a load. When it delivers the current to the load, a voltage is developed across the load. And from that, we know by common electrical engineering that the power being delivered to the load is the product of the voltage times the current. And since we're dealing with DC, the voltage and the current are in phase. So there's no problem of there being a problem like there is in an AC electrical circuit, where we have to take into account a phase shift factor. So basically, because it's a current source, you can drive a load directly, and you need to rethink the concept of how you're going to use this as a power source.
Dr. Yu, I wanted to,
One more thing, and the other thing is, why is it a current source? It's a current source because of diffusion. The last thing in the world that you would think of. In a battery, charges are generated into the electrolyte at one electrode, and they transit to the other electrode. Here, we're using diffusion, not an electric field. And in fact, it is just unusual. That's all I wanted to say. You need to, it's hard to believe that it exists at all, but when you do the measurements, you come to the conclusion that it's different than things you have seen in the past.
Dr. Yu, you're a physicist, and that's why I wanted to have you on for this conversation. We do our Science and Use segment each week, and we do conversations with all kinds of folks doing interesting things. So this is a topic that we have explored a lot over the years, on camera and off camera, researching these concepts of LENR, low energy nuclear reactions, cold fusion as the traditional term was. And now this device that you guys have created, Lattice Energy Converter, right? LEC, that's a good term. I like that. So Dr. Yu, I want you to dive in here with anything you have, questions or anything.
Sure. First of all, I'm totally believe the device you generated and create energy, create a voltage, or you say the current, of course you have an electrical power. I have totally no doubt because there are so many evidence, even in our position, we have a device, with a silicon, with a graphite on top layer and with a silicon substrate base, and you can measure the voltage, just one plate, the laminated plate. There's a voltage of 1.5 volts. So what we did is for demonstration purpose. So we use two plates, this kind of laminated plate. We call, somebody call it as a solid battery. Okay. So we connect them in series, so we can power a LED light. So use LED light to show them, and this two plates, two LED lights, and we left there, for 6 months. The LED lights never off; it's always on. Just like you said, you have 8 years. You're called converter. There's a Lattice Energy Converter, the tube, like a hardware store, the device. You last for 80 years. So I'm totally convinced we can convert generate electricity, use a solid material, and in your case, you use there was a palladium plated, the copper electrodes, right, and put it in the copper cube inside of it, and with the gases, with hydrogen, deuterium gases, you can run for 80 years. I totally have no doubt. The one of the reasons is, so you mentioned about where comes this activation, or called radiation, right? So for me, the fundamental question is, even to the day, people still don't understand what electricity is. Okay, you guys probably will agree. So I know Harper explained in in 1890s or something. Even J.J. Thomson,
1890s.
Yeah, even J.J. Thomson tried to explain the electricity. For me, that's not even correct. So that's why he only won one Nobel Prize, right? So okay, so because we do not understand what electricity is, so that's why we're questioning where comes this radiation activation force, energy, to generate the electricity. So that's why in the what is it called, the establishment physical arena. So they were dismissed the phenomenon. Normally you have to admit the fact, right? Even diminish the fact because the wrong understanding prevailing in the current physics among physics theories, of course, engineering part of electricians. So I just want to share with you what really electricity. Okay, I hope this is an unsolved mystery. Okay, for people, I know you guys have. I read the bio, for Frank, our such an extinguished, biography, and so Harper, and you are such you have a physics major background, and you have such years of the experience. So we especially as electrician, the current understanding electricity is a flow of free electrons, right? Based on that one, so you were questioning what things can generate the free electrons and how electron can flow. So that's all the questions, and that none of them are correct. Okay, I saw the Harper. You want to say something? Yeah.
Yes, I do. You mentioned the free electrons.
Right.
Unfortunately, I believe that this is not a case of free electrons. If we were dealing with a conventional plasma, a thermal plasma of the type that people are using for hot fusion, then we would have positive charges and we would have free electrons. No, in this case, I believe that we are dealing with a ion-ion plasma. We have positive ions, we have negative ions, we have I am pretty sure, a lack of free electrons. And this makes, again, this device somewhat different than your low discharge tubes, which are based on having free electrons because the gas is at low pressure. Here we're running with gas pressures of atmospheric or greater, and at those, the attachment of the ions, of the electrons to form ions is such that there are very few free electrons present. There are probably some very high energy ones, but the ones that have lost their energy due to ionization of the gas, that is the electrons that have been produced by the initial separation of the gas molecule, those electrons, I believe, immediately attach to a neutral gas molecule and form a negative ion.
Yeah.
The other item that I would like to point out is while cold fusion originally started with palladium and deuterium, palladium being a precious metal and deuterium being a rather precious gas, we have shown, in fact, at ICCF 23 in China, we presented a paper where we showed that this phenomenon works for the working electrode being made of iron and the gas being made of hydrogen, so that we now know that we can produce the same LEC phenomenon without using either precious metal or precious gas.
Yeah, in fact, this is one of the reasons we believe metallurgy is most important. At this point, every metal hydride that we have tried has worked. Now, that's only two at this point.
However, the LENR community has done a significant amount of work on nickel and hydrogen.
Yeah.
And so if we take the standard community, we know of a third one that works.
Yeah, so we suspect that a lot of metal hydrides might work, and that, of course, reduces the cost and increases availability, and we believe opens the door for much improved performance.
Yes. I just want to say, so you said that in this case does not involve the free electron, which I would say the so-called free electron never existed. It does not even exist. So the electricity have nothing to do with the flow of free electron, because free electron does not exist. So I just want to say, you just said, oh, so a plasma, generated have nothing to do with electron. People would think you crazy, right? Because how, if no free electron, how can you generate electricity, the current with the plasma? because the concept of current is a flow of electron, free electron. Is that right? So I actually agree with you. There is no free electron. So electricity have nothing to do with the free electron, because the free electron does not even exist. So what is really here is I try to say something deeper than current. Why people have a confusion? Oh, sometimes it's a voltage, sometimes it's a current, sometimes it's a free electron, sometimes a plasma. The so-called electron is a vibration of ionized particles. It's a vibration. There nothing flows. So whenever you can, so how can you generate a vibration? So now you have a plasma field. What has a plasma have a high heat? Of course, the particles moving, right? The heat particle. So you create a moving magnetic field. When you plasma field, you're moving magnetic field. Whenever you have a vibrating, moving magnetic field, what happens? You create the magnetic particles. The particles in the conductor. You create the motion, the vibration in the conductor. And that conductor, the motion of conductor vibration, that's where you measure voltage. So when you have the device called, what is the converter?
LEC.
Yeah. Yes, you Lattice converter. So where energy? You have a gases inside of constantly reacting with palladium, the electrodes, right? You have a counter electrode, and you use gas. What's the wonderful things about the gas than liquid? You mentioned the precious metal, and the precious, the deuterium, like a precious gas, and the deuterium, your heavy water, right? Those actually gas easier to vibrate, and that's why you have the liquid gas medium in the converter, right? In your lattice converter. And whenever you have a temperature change, and whenever you have external lights and anything, environmental change, vibration, the gas will be very active inside. When you have active gases motion, you will create the vibration, you will create the voltage. So that's where electricity energy come from. If so, you can save, put it. I don't know if you save it in the refrigerator. You're cooling them. You probably still have a voltage, but the voltage might be less than that. Have you tried to use measure voltage during the winter time and during warm temperature? Have you tried this one?
We have varied the temperature from minus 55 degrees centigrade.
Okay, yeah.
To 100, yeah. And the reason we did that was we were concerned that were we actually seeing conduction from the humidity in the gas, and so by cooling it, we packed the cell in dry ice and had a thermocouple there, and minus 55 degrees C, it worked just fine. So, and also we know that the gas is required. Bavarian, the French professor who replicated, he did some experiments where when he pulled the vacuum on the cell, the effect went away. The gas has to be in the cell, so something is ionizing the gas.
That's the medium we need to oscillate, to vibrate. Without the vibration, it is not going to work. And so the gas is such a. Now I find out. So the gas medium is much better based on what you said. Seems like much better than liquid. This medium. Wow.
And it allows us to go to the higher temperatures where we can get the greater power.
See,
because the power increases exponentially as we raise the temperature.
David, did you hear that one? That's exactly what I predicted. Higher temperature, you create a higher motion, right? Then you generate higher electricity. So why this higher motion? Sometimes people will say, "Oh, you may be with the plasmalized, high temperature plasmalized things, so maybe plasma motion." Nothing, doesn't matter, whatever. As long as you have a charged particle in motion, the higher the voltage, you make the higher amplitude of vibration, frequency, of course you have a higher electrical output. You have a higher power. So these are
So-
all consistent. Yeah.
Okay, yeah, the other thing that happens at higher temperatures is the number of vacancies go up exponentially. And we believe that vacancies are very important for the production of whatever it is that is ionizing the gas. Something has to, if we were only ionizing the gas by temperature, Saha showed that you have to be above about 2000 degrees C,
Kelvin.
or 2000 degrees Kelvin, before you have enough motion, vibration motion that the collision itself will ionize the gas. We're obviously nowhere near that. So something is ionizing the gas. Once you have the ionized gas, then a lot of things can happen. And the variables you just talked about are certainly ones we've talked about. But in addition to that, increasing the temperature also increases the number of vacancies. And in fact, we've seen that the output goes up as the cube of the temperatures. That
Yes. You know why? Because we mentioned about it. This was lower pressure. Lower pressure, you have more vacancies, right? The lower pressure help you.
Yeah.
Because you need the vibration amplitude, the difference, the delta difference of vibration is higher. You cannot say if I have a high pressure, so high pressure, so then no vacancy, the relative delta pressure difference is not high. So that does not help you. In this case, you said we lower temperature and we will create a more higher output. That's the reason. You want the most efficient level of density to create a free vibration. That's where electricity created. When you have a free vibration of a charged, the plasma medium, charged particle, what happens? Create the motion in the conductors. The particles started vibrating. So that's where energy is. I believe we are totally agree. So the theory agrees with your experiment, with your experience. You said 8 years and you observed this one higher. You said higher temperature increase the temperature of the gas. You see exponentially increase output. I have no doubt it. And also you mentioned about we reduce the pressure instead of use higher pressure. So now you said well, you need the vacancies, right? So that's why it helps increase free vibration. That's where you're lasting forever. Okay. Do you
Okay.
agree? Do you agree? There is no free electrons whatsoever in the world.
Yeah, I'd like to make a suggestion.
Okay.
It's been called cold fusion. We'd have no idea whether it's fusion or not. Of course, that's an open question. It's
Right.
been called low energy nuclear reactions.
It's better. Yeah.
I like to keep the acronym LENR
Yeah.
and call it Lattice Enabling because I believe
Lattice enabled. Okay.
because I believe that it is the entire properties which go back to the metallurgy. It is the interaction of the occluded hydrogen within the lattice of the working electrode that makes this whole process possible. If you do not have the hydrogen occluded, it does not work. Hydrogen by itself does not work. You have to have the combination of the lattice and the hydrogen.
Okay. My question is what the lattice means here?
What? I didn't understand.
Oh,
What is-
okay. So, the lattice, so you wanted to make this the same, short notation, right? LENR to be lattice enabled. Okay. So what does the lattice here represent?
The lattice represents the hydrogen host material, which occludes the hydrogen, and it is the interaction of the vibration, of the thermal vibration of
Yes.
the lattice material with the occluded hydrogen. And that we believe, as I said, we don't know what the physics is that gives rise to the radiation, but it seems at this point in time, it's strongly suggestive that it is a complex interaction between the thermal vibration of the lattice and the occluded hydrogen that gives rise to the phenomenon.
Okay. So I can explain one thing. One thing I as number one, hydrogen does not form lattice. Okay, it's not like a solid lattice structure. I'm talking about even water. Water is a layered lattice. Hydrogen, you have a is hydrogen molecules with two hydrogen atoms, right? So does not form lattice. Lattice, you have the three-dimensional shape. So that's why I saw that the lattice, the name of lattice here may not express your really fundamental reason for your device. So I do not see lattice part. Yeah.
We believe that the hydrogen is atomic hydrogen in the lattice. It's not the hydrogen molecule. It's H plus.
So are you talking about the liquid form or a solid form of hydrogen? That would call that to me, I would have a lattice shape in my mind.
We're talking about the occluded hydrogen within the lattice, a la what Graham proposed many years ago, back in the 1860s, when Graham studied the occlusion of hydrogen in palladium when he was director of the Royal Mint. And it is, as most of the people at LENR agree, you need to have a certain amount of hydrogen occluded in the material, normally palladium, in order for the phenomenon to occur. And so it's the occluded hydrogen that is what is reacting to form the radiation. We don't know how. We have no idea how it does this, but it appears, at least from the measurements and from the observations, that these are two things are required. One, that you have to have a hydrogen host material that will essentially occlude hydrogen, and iron, nickel, palladium. These are typical metals that occlude hydrogen, and these are the ones that seem to work.
Okay, so you think about the lattice is there's hosting material, right?
The host material, hydrogen host material, we call it.
So the metal is that lattice, not the hydrogen, right?
Yeah, the metal is the lattice.
Well,
so that's the issue there.
Okay. So
yeah, hydrogen is, and I'm not a chemist, but hydrogen it actually forms a metal hydride, and some of the bonds I think are different or whatever, but in any event, the hydrogen goes into the interstitial locations in the lattice.
Okay, so now I understand. So where the energy come from? Solid lattice is there are energies stored in solid lattice shape. I have no problem, but the key is how to release this energy, right? So-called release energy to make them vibrate, right? Now the hydrogen atoms come in. Hydrogen atom is the smallest element in the elementary table, right? Periodic table. So that's why the hydrogen can kind of stick into the lattice shape of a metallic material. What the hydrogen atom do? Weakening, they are bound. When your weakening bond become radioactive materials, right? Radioactive materials have a very loose bond, so that's why it is so easy to eject particles, from the bond and to create the radiation. Yeah, so that's what. So you just talking about that. So where comes this radiation? That's where I'm trying to explain this one. The hydrogen gas interact with this lattice, the solid, the hosting material interaction, and the interaction create a vibration, and that's where you can measure electricity. Instead of in the old days, Harper mentioned about why they call the cold fusion excess of heat. These are from the 1890s. Those are steam engine type. When you create the heat, you create the energy. Nowadays, we call the energy electrical energy, the most simple one, right? So that's why if you can direct measure voltage and the current, get the electric power, that's where the clean energy is. That's where we know we can drive all the electronic appliance. So you are definitely on the right path. Forget about the heat. We try to avoid the heat. We try to get direct energy. so direct electricity out of any device, and your device, two of them are both offer the difference of power. But based on what you said, the plates we have, it can generate 1.5 volts and a couple hundred milliamps. So compare with yours. So seems like so we can drive. We use the two plates can drive a LED lights. So how many of them do you think if we put in series can lit up a LED light? That's a 3 volts LED light. How many of you have the little called the new cell, the cell piece, right? So
this is where one of the challenges, the fact that it's a current source rather than a voltage source, how you put them together. And for example, your solar panels, they have micro inverters at each panel now, because one dead solar panel can wipe out a whole string.
Right.
And so anyhow, the idea of just stacking some of these together and connecting them heel to toe or whatever the way you think about a voltage source, it may not be the right way to do it.
This is a good point. Let me explain the difference between in this case, so called a voltage source or called a current source. I believe the common people, even electrician, may not even use this term. So without the current, where can you come have the voltage, right? Without the voltage, how can you come electric flow, right? So the current. But I understand that when you talking about the current source versus the voltage source, if you use your solar panel, if you can put a solar panel in series, you get a higher voltage. So in that series, you get a voltage source. So where comes the current source? If you have a parallel, you side by side have a lot of those series. Now you becomes what is the current source. You said I do not need to connect. Say you said what is 1/6 of a volts. So basically you need what is 20 of them. 20 of those little cells connect in series in order to lit up a LED light. So that's 3 volts, right? But if you just need that one, now besides of this just one series one, you have millions of series. Now you becomes what is that? Becomes like a parallel. So now you do not increase voltage, you only increase current. So now becomes current source. I hope that makes sense. I know these are the questions that never been answered in my life. I never see any people understand what is energy source and voltage source. What's the difference? Because under current concept, if they do not understand the electricity, say flow of electron, which does not even exist, if they use that concept, they can never solve this one problem. Does that make any sense to you?
Well, one of the things that we've talked about is how do we light an LED? Because that would clearly be a very convincing demonstration. And that's where we run up against how do we string these together and what do we need to do? And we've given some thought to, what sort of electronics do we need to?
You don't need it. You don't need an additional one. You just put the connection, put them in series. Because in order to light up a LED light, you need to have a voltage, at least 3 volts. However, just 3 volts, because your current is so low, just enough voltage may not enough. Now you have a parallel, multiple one, and increase current enough. So then you should be able to light. So that's my prediction for you. If you follow me, I believe you would lit up a LED light in no time. So maybe you should try that.
That's what we're working on now. We feel that would be the next step that would make people believe in this technology is that we could light an LED.
I think you already have the device. It's already much advanced. You said the order magnitude higher than previous one. I believe you should be able to light up the LED light. Follow my explanation. Number one, you have to make each connect your new cell. Each reach to 3 volts. Now you have a parallel one. Put as much you can try to 3, 5, 10. Put a parallel until the lights shoot up. And I'm waiting for your good news.
Okay, let's go
So
back now and ask, are there any more questions that about the operation or something that we need to address?
I just have one question. I thought, why you have one device worked for 8 years? So why you change the direction a little bit, try to create this new product called the fuse the new cell. So what the motivation behind that?
I think you're talking about why are we doing to this?
Right, you already have a product, right? Why not perfect it?
Well, the problem is that product that we have, you know, if I want to package several of those together, it takes a lot of volume. It's not, you don't get a good packing fraction that way.
Oh, not efficient. Okay, got it.
This way, you know, if I can have a panel here that's, let's say, a square foot,
yes,
a little larger than a square foot, which is 1,000
cost
square,
lower and
Yeah.
easier to scale
And-
up.
and it's only, if it's only 3 or 4 millimeters thick, you know, I can, in a stack this high, I can have 40 or 50 of them, you know, so that's why we
Went to the new geometry.
went to the new geometry.
So basically, you just tell me this is a better product than the other one.
Yeah. So, yeah, the other was good for demonstration, and we've learned a lot from the other cell. but
The
this-
other one, I believe the other one has an industrial scale usage. Yeah, even though, yeah, right now you said that, you know, you stack them up, but that have its own usage too. So, but this one were very easy for you to demonstrate, you know, how effective. This is basically is a solid state battery. That's what you generate. You stack them up. Of course, you have to parallel instead of only series and parallel. And you could generate as much as a voltage and as much as current as you want, theoretically. Of course, practically may be different.
So what do you guys need to move forward? What do you guys need to scale up to industrial scale or something, or powering a house or something that would be a benchmark for a revolutionary technology?
Well,
And by the way, I'm looking for a photo I'm going to try to share with you. So if you see me glancing at my phone, I'm still
Okay.
listening.
okay. You know, metallurgy, I think, is the primary thing. And for example, you know, here we've got this thing, which is nominally a little less than an inch in diameter, the opening in this, which is 3 or 4 square centimeters. I've got I'm of two minds of thought here. One is, should we go smaller, and even down to particulate? In fact, we have experiments where we've seen that particulate will work, and this will produce ions without actually being part of the electrical circuit. So we may go, you know, that's one way to go, and then and have a lot of these individuals. So in order to stack them up, it's more of a solid state electronics technology that would help get us to that point. So anyhow, the metallurgy, I think, is the big area that we're looking for now, and in doing that, we're looking for people that may have expertise and facilities in that area that we don't have. You know, we can go to the hardware store and buy pipe. Going to the hardware store, you probably can't buy some of the solid state electronics devices that we would like to use or to modify to use. So
Okay, I would like to address a different question. Everybody wants this to be a battery. As I said, it's a current source. They want it to be a battery. We know how to make it into a battery, and that's been known for a number of years. And what you do is you take two dissimilar metals and you simply put the ionized gas between the two dissimilar metals. And this goes by the name of a contact potential difference battery. And it doesn't require that the working electrode be part of the circuit, as Dr. Gordon was just describing. We think that if we go to that geometry, then the device will become more usable in the community because it will now behave more like a battery, and people know how to use batteries rather than the current source that we currently have.
and we have cell designs where we have done the contact potential difference battery, where we have copper and zinc and plates and ions are created in between those plates by the palladium, and we can measure the difference there from the contact potential difference. So that has some other advantages too. In the, we don't have the shunt current issues. There are, anything you can do to reduce the transit time between the plates so you have less time for the ions to recombine. There are lots of things that we can do in the design that we believe will help improve the output.
So that's basically what we're looking at then, is improved metallurgy and improved engineering.
Are you guys self-funded, or are you looking to raise capital to get to that, or where are you guys at with that?
We're self-funded, and at this point, we're looking more for partners than we are for us to raise money and set up a lab and hire people and everything. We're supposed to be retired. I'm reminded of that by my wife periodically, but and I think that would take a long time. And I believe there are people out there with the right expertise, and in fact, groups of people with the right expertise that we would like to work with and have them bring their expertise and their facilities in and into the field. So anyhow, that's what we're looking for at this point.
You're
A little
looking,
money would be nice, but we're funding everything. We're paying everything ourselves at this point.
and are you guys referring to like other LENR teams that are currently in the game that you want to work with for this, or?
We're doing some of that now. There are companies and others that are getting interested now because of the conference. ICCF 24, I think, was a very successful conference, and companies that had been afraid to spend money on this kind of research because they were afraid their stockholders would say, you're wasting money. How come you're doing that? All of a sudden, their fact is coming out that that's a double-edged sword.
Mhm.
And if you avoid spending money on this area and there's something there, then your stockholders could come at you and say, why didn't you do this when it was obvious? So I believe that there will be a lot of companies getting interested in this. As they announced at the conference, ARPA-E, which is from the Department of Energy, hopes to have an announcement, a broad agency announcement or something out sometime this month, announcing funding for work in this area. We don't know any more about it at this point. At the conference, there was discussion of setting up an X Prize sort of approach of $100 million to see if companies will jump in on that. The organizer of that said something I found interesting. He said a lot of companies don't want to participate in that because they don't want to come in second. And if you come in second, you just spend a lot of money and you don't get anything. I don't think you need an X prize. If people see the dangle is carrot out there, you could come in 10th if you were a company and still make a lot of money. If, you know, there's the market for this is so huge, if it works. So anyhow, I think we need, you know, you hear the term critical mass in a lot of nuclear reactions, and we kind of have to achieve critical mass in this area so that enough companies will come in. And I believe, you know, the fact that the government may be starting to put money into this, I think will entice a lot of companies all of a sudden to say, we need to spend some of our own IRAD money, and what do we have that might give us a proprietary advantage as far as their current skills. So anyhow, those are the kinds of things that we would like to do and see. That's what we would like to see.
And I'd like to say it a different way, say it slightly different way. We have not tried to keep this material proprietary. We are willing to share it with anybody, any company who is interested in trying to develop this. We will be more than pleased to share the technology and knowledge that we have with them, because we think this would be good for the country and good for people.
Yeah, we do have 3 patents, and of course, those patents we may or may not actually be worth something at some point in time, but they're only worth something if somebody starts building products. And so it's in our best interest if we can get people to start building products and developing this technology. And several years ago, I think Jed Rothwell, one of the people working it, pointed out that once people get on board and figure out this is going to work, the development could occur very quickly, because unlike the transistor, which took 20 or 30 years, you had to develop a whole solid state electronics industry. It took the cost of initiation to get involved was expensive, because you needed expensive instruments and equipment. You know, as you've seen here, we've done it with parts from the hardware store, and so the opportunity to get thousands of groups working on it is I think very, very possible that could happen.
Yeah, I think it's exciting what you're doing, and I thank you for your tireless efforts during your retirement time. You're supposed to be in Hawaii right now having a pina colada. Instead, you're trying to change the world. Look at you. That's great.
Yeah, well, San Diego's not that much.
Okay, that's true.
Hawaii. You know, we're not we're not.
So you're okay. You got a pina colada down the road, don't you? Yeah.
Yeah.
Well, you guys are doing wonderful work, and you know, I think I have to tell you something. You know, I think, you know, from your generation, one thing that's kind of bittersweet about this is, you know, I look at that ICCF conference, and I see a lot of people in your age group leading the charge on this stuff, and it's a sad statement for our culture that people my age, I'm in my 30s, that more people in my age are not in this space talking about LENR and cold fusion. And I think it may have something to do with what happened in our culture. I mean, you guys probably grew up with science fiction and stuff talking about going to the stars and Flash Gordon, and you guys probably grew up with that kind of forward thinking mentality in our culture that we can achieve great things. We can, you know, we can use science in a positive direction. My generation grew up, you know, basically with this idea that, oh, we've reached the end of history, all the things, and, you know, everything in the physical material world has already been pretty much figured out. Everything else now is about information, right? And computers are fine. But what happens is people in my generation, all the great minds are going off to create apps, because that's where all the capital is flowing. That's where the energy is. It's not really where it should be, though. I think there are questions that remain to be answered in the world of the atom. And that's one of the reasons why I've spent so much time with Dr. Yu, because I do believe, and I know this is not your place, because your place is to develop a technology. So you're not here to try to reinvent physics. But I do believe that the establishment version of physics has kind of run its course, that Thomas Kuhn talks about this idea that scientific paradigm shifts happen when enough anomalies start to pile up one after another that the current scientific paradigm does not give an adequate answer for. And I think that this stuff that you're doing, along with a bunch of other different anomalies that we could get into, are those anomalies piling up, demanding for a new physics that can have a better explanation with the data that's presented to us. It's kind of like what happened when we had, Copernicus versus Ptolemy. I mean, Ptolemy's work was being used to chart all over the seas on ships, but it was still wrong. It's still wrong. You can have a wrong physics model that is a gerrymandered thing that you can kind of jerry-rig to make it work, and you're still sailing in the dark. But when you have a simplified in Occam's razor, giving a simpler explanation for the same anomalies that the current model doesn't quite give a sufficient answer for, when you can have that new map, then you can chart a course to the new world without bumping into dead ends and chasing your tail. So that's what I think new physics is important to do here. And I'm not saying that, that's not your field of looking at, but that's why I wanted to have you interact with Dr. Yu, because he's someone that works in establishment field of physics and also has an engineering background, but is not afraid to challenge the sacred cows of what is considered to be settled science. I don't like that term, settled science.
Okay, well, yeah, one of the things that has piqued my interest because of this, we've got a cell that spontaneously self-initiates and self-sustains the production of a voltage and current. And people think, well, low energy nuclear actions, that started in 1989 with Pons and Fleischmann. I'm not sure about that. I think that maybe a lot of biological transmutations, we may have a lot to learn there. And about half of the oxygen that we breathe now comes from diatoms in the ocean. And they sequester the carbon and release the oxygen. How does that happen? It's spontaneous, self-initiation, self-sustained. No one's there applying a potential or doing anything like that. And that's just one example. John Paul Bavarian, who is one of our replicators, wrote a book on fusion in all of its forms. And he spends a couple of chapters talking about biological transmutations and things like this. So there may be a whole new field out there that has basically been shut down because people say, well, can't be, it doesn't fit our current theory.
I'd like to make a comment that I believe that part of the problem these days is lack of multidiscipline education. If anything, some of the success that we've had has been the fact that we have looked at this from multiple points of view, from the physics, from the mathematics, from the electrical engineering, from the mechanical engineering. If you focus too narrowly, and many of our educational systems today are very narrow in their structure. And I just make the comment that if I had something to tell the young children today, I would say, try to broaden your education, and STEM, science, technology, engineering, mathematics. It's maybe a dirty word to those who believe in the arts, but a STEM education, I think, will do many a person, male or female, well in life.
Well said. Very good.
Well, good. You guys have done a great job, and I feel like you guys are like pioneers. You've landed on a new land, a new world, and the old physics model is telling you that you've made it to India, but you've actually made it to a new world. So we got to get the physics updated to catch up to what you guys have discovered with your exploration. So hopefully we can be of any help. Let us know, and we'd be glad to help. And Dr. Yu, any final thoughts or questions or anything?
I think you're really onto something big. So keep working on. I think with the connection, as I believe, David or some of his friends might be able to offer some help. Yeah.
Yeah. Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.